1.5 billion years ago, somewhere in a distant galaxy we will never see, two cosmic monsters were orbiting each other. Each of them weighed the equivalent of 30 suns, but compressed into an object so dense, so dark, so absolute that nothing escaped from it, not even light. They had been approaching each other for millions of years, barely slowing, but inexorably. And then, in barely a fraction of a second, they merged. The explosion produced no light, no flame, no visible shockwave, but space itself trembled. Space-time, that invisible fabric on which stars, galaxies, planets, and every atom of your body are embroidered, crinkled like the surface of a lake into which someone had thrown an enormous rock. And that ripple, that cosmic shiver, traveled for 1.5 billion years through the deepest void of the universe, crossing billions of galaxies, to reach, in September 2015, a small blue planet, lost in an ordinary suburb of the Milky Way. It passed through the Earth. It passed through you. Your body compressed and expanded slightly for a brief moment. You felt nothing. Nobody felt anything. But an instrument, designed by thousands of scientists over decades of obstinacy, captured that whisper. And that whisper changed everything. What you are about to hear is the story of the greatest act of cosmic eavesdropping in the history of humanity. The story of an idea born in a Berlin office in the middle of a world war, of an instrument so sensitive it can measure a distance billions of times smaller than an atom, and of a September night when the universe finally decided to speak to us. And what that conversation reveals about the nature of the cosmos surpasses everything we thought we knew. Before we go further, if you enjoy the great questions of the universe and the mysteries science is just beginning to decipher, subscribe to the channel and hit like. It really helps us keep going. And in the comments, tell me, which city are you watching this from? And what time is it where you are right now? In the description, you'll also find a link if you'd like to support the channel's development with a donation. Now, to understand what gravitational waves are and why they changed everything, we need to start with something you think you know. Space. You think space is a backdrop, an empty, rigid stage in which stars and planets move. A motionless, silent, neutral void, like a movie theater in which actors move freely. For centuries, this was the dominant view, and Newton himself saw things no differently. For him, gravity was a mysterious force acting at a distance, instantaneously, as if two objects were pulling each other through an absolute void. This view worked. It worked very well, in fact. It allowed us to calculate planetary orbits, predict eclipses, navigate the oceans. But it had one flaw. It said nothing about how gravity propagated. And with Einstein's special relativity in 1905, a fundamental problem emerged. In Einstein's universe, nothing can travel faster than light, not even a gravitational signal. If the sun were to suddenly vanish, the Earth should not feel its absence instantaneously. It would have to wait. But for how long? And how? To answer these questions, Einstein spent 10 years developing something radically different, something that would reshuffle all the cards in physics. His theory of general relativity, completed in 1915, proposed a revolutionary idea. Gravity is not a force. Gravity is the curvature of space-time itself. Here is how to understand it. Imagine a large rubber sheet stretched horizontally, a perfectly flat, perfectly smooth sheet. Now, place a bowling ball at its center. The sheet sags. It deforms around the ball. If you roll a small marble across that sheet, it will no longer travel in a straight line. It will follow the curvature of the sheet and move toward the ball, not because there is an invisible force pulling the marble toward the ball, but because the sheet itself is curved. In Einstein's universe, that sheet is space-time, and planets, stars, galaxies, every massive object deforms that sheet around it. The Earth does not fall toward the sun because a force pulls it. It falls because it follows the natural curve of space-time that the sun has created around itself. What you call gravity, the force keeping you on the ground right now, is nothing other than you following the curvature of space-time created by the mass of the Earth. This idea is already dizzying, but Einstein did not stop there. If massive objects curve spacetime, what happens when those objects move? If you move the bowling ball across the rubber sheet, the deformation moves with it. But on an elastic sheet, that movement creates ripples, undulations that propagate through the fabric. Spacetime is elastic too. When a mass moves, and especially when it accelerates, the curvature it creates propagates in the form of undulations. These undulations are what we call gravitational waves. They are not light, they are not particles, they are not sound. They are ripples in the very structure of space-time, traveling through the universe like circles on the surface of a pond. And when they pass, they do something extraordinary. They alternately compress and stretch space in the directions perpendicular to their travel, in two directions. If a gravitational wave passed through you right now, your body would lengthen slightly in one direction and compress in the other, then the reverse, then again, at a regular rhythm. It would be a strange experience, except that you would feel absolutely nothing, because the space-time in which you are immersed deforms uniformly. Your body, your atoms, your measuring instruments, everything deforms at the same time. Measuring the deformation is where the true challenge lies. Space-time is therefore not an empty, rigid backdrop. It is a dynamic, living fabric that vibrates to the rhythm of the most violent events in the universe. And to understand how we manage to hear these vibrations, we must first understand where the idea came from. We must go back to Berlin in 1916. The year 1916 is not a good year for humanity. Europe has been at war for 2 years. The trenches of Verdun had just swallowed hundreds of thousands of lives in a matter of months. And yet, in a Berlin office, an exhausted and ill man, not yet 40 years old, had just published one of the deepest theories ever produced by the human mind. Albert Einstein had submitted the final equations of general relativity to the Royal Prussian Academy of Sciences on the 25th of November, 1915, and the paper was published on the 16th of March, 1916. Barely had the ink dried when Einstein began exploring the consequences of his own equations. One of those consequences he discovered almost immediately. His equations, when solved in the case of a weak and variable gravitational field, produce solutions that resemble waves, disturbances of space-time that propagate at the speed of light, undulations in the deep structure of reality. Einstein understood what this meant. If a mass accelerates, it must radiate energy in the form of gravitational waves, exactly as an accelerating electric charge radiates energy in the form of electromagnetic waves, light. This is a deep symmetry between two fundamental forces of nature. But from the very beginning, Einstein had doubts, and he had good reasons to doubt. The problem was subtle but fundamental. In general relativity, one can always choose a different coordinate system to describe the same spacetime. Some things change depending on the coordinate system used. Einstein, therefore, wondered whether the gravitational waves he found in his equations were real physical undulations of space-time or simply an artifact of the coordinate system he had chosen. Waves that exist in the equations, but not in reality. He would change his mind several times. In 1916, he told the physicist Karl Schwarzschild that they did not exist, then published a paper saying they did. In 1937, he co-signed with Nathan Rosen a paper claiming they did not exist. This paper was rejected by the journal, which submitted it to revision, something Einstein took badly. But the revisions forced the authors to acknowledge a calculation error, and the paper was ultimately published with the opposite conclusion. The waves do indeed exist. This debate stretched over decades. It was not until 1957, at the Chapel Hill Conference in North Carolina, that the question was definitively settled. Two physicists, Felix Pirani and Hermann Bondi, demonstrated rigorously that gravitational waves have a physical reality. Bondi used an argument that has since become famous. Take two beads threaded on a rigid rod. If a gravitational wave passes through, the beads will move relative to each other and create friction on the rod. That friction produces heat. And since energy is conserved, that heat must come from somewhere. It comes from the wave. Therefore, the wave carries real energy. Therefore, the wave is real. This simple reasoning, known as the sticky bead argument, closed the debate. But even when Einstein accepted the existence of gravitational waves, he was convinced of one thing: we could never detect them. Space-time is incredibly rigid. To make it vibrate by a measurable amount, you would need cosmic events of an absolutely unimaginable violence. The Earth orbiting the Sun does emit gravitational waves, yes, but their power is that of a small light bulb. The passage of these waves through a detector would produce a completely negligible change in distance. Einstein thought the problem was insurmountable. He was wrong, but it would take a century to prove it. And even before direct proof, there would be an intermediate step, an indirect proof so perfect that it earned its discoverers a Nobel Prize. That proof lay deep in the Milky Way, hidden in the impeccable ticking of a dying star. In 1974, the American astronomer Russell Hulse was searching for new pulsars with the Arecibo radio telescope in Puerto Rico, the largest instrument of its kind in the world at the time. A pulsar is a rapidly rotating neutron star, an object as dense as a mountain compressed into a sphere a few kilometers in radius, that emits a beam of radio waves with each rotation, like a cosmic lighthouse. This radio ticking is extraordinarily regular, more precise than the finest atomic clock. That is why pulsars are so valuable to physics. That day, Hulse detected a strange signal. A pulsar, yes, but one whose period oscillated. It sped up, slowed down, shortened, lengthened, periodically. Hulse quickly understood what was happening. This pulsar was not alone. It was gravitationally bound to a companion, another neutron star, and the two were orbiting each other. When the pulsar moved closer to us in its orbit, its signals arrived faster. When it moved away, they arrived more slowly, like the siren of an ambulance that changes pitch depending on whether it is approaching or receding. It is the Doppler effect applied to radio waves. Hulse informed his thesis supervisor, Joseph Taylor, and together they began observing this system. What they discovered would lead them, 20 years later, to Stockholm. The two neutron stars were orbiting each other at a distance comparable to that between the Earth and the Moon, but at prodigious speeds. Their orbital period was about 8 hours. Each star weighed roughly 1.5 times the mass of our Sun, and month after month, year after year, Taylor and his collaborators measured the orbital period of the system with increasing precision. They then discovered something remarkable. The orbit was shrinking. The two stars were drawing closer to each other. Their orbital period was decreasing. The system was losing energy. And the question was, where was that energy going? The answer, when you apply Einstein's equations, is clear. The system was losing exactly the energy it should lose if it were emitting gravitational waves. Not approximately, not within 10%, exactly. The measured curve of the orbital period reduction matched the curve predicted by general relativity to a precision exceeding 1/100%. It was an extraordinary confirmation. Granted, no one had yet directly detected gravitational waves, but their effect on this binary system was visible through their energy signature. Taylor and Hulse received the Nobel Prize in Physics in 1993 for this discovery. The scientific community was convinced. Gravitational waves exist. All that remained was to hear them directly. But to do that, something would have to be built that was absolutely without precedent in the history of human engineering. The orbit of the Hulse-Taylor system continues to shrink. In 300 million years, the two stars will merge. It will be a violent, brief, and extraordinarily powerful event, and the gravitational waves that result could be detected from Earth. But for the time being, in 1974, the question was not whether gravitational waves exist. The question was, could one build an instrument capable of measuring them directly? And that question, at the time, seemed almost absurd. The problem is this: when a gravitational wave passes through a detector, it deforms space. It stretches distances in one direction and compresses them in the other. But by how much? Even for the most violent cosmic events imaginable, such as the merger of two massive black holes, this deformation is ridiculously small. If you took a detector arm 4 kilometers long, the most powerful gravitational wave ever detected would have deformed that arm by an amount far smaller than the nucleus of a proton. To give you an idea, if you could place a detector between the Earth and Proxima Centauri, the nearest star to us at about 4 light-years away, a typical gravitational wave would deform that distance by roughly 1 centimeter. And even then, The source would have to be very close and very powerful. Measuring such an infinitesimal variation in a device 4 kilometers long, in a world where trucks rolling a kilometer away make the ground vibrate, where earthquakes arrive without warning, where temperature changes expand and contract materials, where quantum fluctuations of light itself introduce noise, all of this seemed to belong to the realm of dreams rather than engineering. And yet, people tried. The first to attempt it was Joseph Weber. In the 1960s, this physicist from the University of Maryland had the idea of building large metal bars, aluminum cylinders weighing roughly 1,000 kilograms, suspended in a vacuum to isolate them from external vibrations. The idea was as follows. If a gravitational wave passed through the bar, it would compress and stretch it slightly. If the frequency of the wave matched the natural resonant frequency of the bar would begin to vibrate, like a tuning fork that has been struck. Sensors attached to the bar would convert this vibration into an electrical signal. Weber placed 2 of these bars at 2 different sites, separated by about 2,000 kilometers. The idea was that if both bars responded simultaneously, that could not be due to local vibrations, but to a common signal from space. In 1969, Weber announced he had detected gravitational waves. The scientific community briefly erupted. Then other teams tried to reproduce his results. Nobody succeeded. Weber had apparently made errors in his statistical analysis. His bars were simply not sensitive enough to detect real gravitational waves. But his work had planted a seed. He had shown that the idea of directly detecting gravitational waves was not entirely absurd, and he had inspired a new generation of physicists. Among them, an MIT researcher named Rainer Weiss. Weiss had approached the problem differently. Rather than using a resonant bar, why not use light itself as a measuring ruler? Light, traveling at a constant speed, could be used to measure tiny variations in distance with a precision far beyond anything a metal bar could offer. Weiss sketched the broad outlines of a revolutionary instrument, a laser interferometer. The principle is as follows. A laser beam is split in 2 by a semi-transparent mirror. The 2 half beams are sent in 2 perpendicular directions, along 2 very long arms. At the end of each arm is a perfectly reflective mirror. The light bounces back and forth between the entry mirror and the end mirror many times to accumulate distance. The 2 beams are then recombined. If the 2 arms are exactly the same length, the 2 recombined beams will cancel each other out. This is called destructive interference. You see black. But if the length of one arm changes, even by the tiniest fraction, the 2 beams no longer cancel perfectly. A light signal appears at the output, and that signal is proportional to the change in length. The stroke of genius lies here. The instrument is tuned so that, in the absence of a gravitational wave, the 2 arms cancel perfectly. You live in absolute darkness. If a gravitational wave passes through, it stretches one arm and compresses the other. The balance is broken. A signal appears, and the shape of that signal, its duration, its frequency, contains all the information about the event that produced the wave. This is the principle at the heart of LIGO, the Laser Interferometer Gravitational Wave Observatory. 2 detectors built in the United States, one in Livingston, Louisiana, the other in Hanford, Washington, separated by about 3,000 kilometers. Each detector is an L-shaped interferometer with 2 arms of 4 kilometers each. But those 4 kilometers are deceiving. Thanks to a system of optical cavities in which light makes hundreds of round trips before being recombined, the effective distance traveled by the light is 1,600 kilometers per arm. It is like having a giant interferometer of 1,600 kilometers in each direction, without needing to dig a tunnel through the globe. For this instrument to work, a series of engineering problems must be solved, each of which seems insurmountable on its own. First, the mirrors must be isolated from all external vibration. A truck rolling 10 kilometers away makes the ground vibrate far more than the signal being sought. LIGO's mirrors are suspended on quadruple pendulums, a series of 4 suspension stages that dampen vibrations progressively. At the last stage, the mirrors weigh about 40 kilograms each and are suspended by threads of fused silica glass, finer than human hair, but remarkably strong. This system is so effective that the environment around the mirrors is quieter than if they were floating in space. Next, The most perfect vacuum possible must be created in the tubes housing the laser beams to prevent air molecules from deflecting the light. The LIGO tubes contain a vacuum whose pressure is far lower than that of interplanetary space. It is one of the largest evacuated volumes in the world. The mirrors themselves are polished to a precision without equal. Their surface is so smooth that if enlarged to the size of France, the largest irregularities would be bumps only a few centimeters high. And the laser itself must be stabilized with extraordinary precision. Its power fluctuations must be kept well below the level of the signal being sought. All of this comes at a price. LIGO is the most expensive project ever funded by the American National Science Foundation, with a total investment exceeding $1 billion. But before arriving at this result, it took decades of a path strewn with obstacles, disappointments, and an obstinate faith in something no one had ever heard. Rainer Weiss, Kip Thorne, and Ronald Drever are the founding fathers of LIGO. Weiss brings the idea of the laser interferometer and the rigor of an engineer who knows every possible source of noise. Thorne brings the theoretical vision and the conviction that astronomical sources are powerful enough to be detected. Drever brings crucial technical innovations, notably the Fabry-Perot cavities that allow light to make hundreds of round trips and accumulate the necessary sensitivity. In 1992, they formally founded the LIGO collaboration with the support of Caltech and MIT, after years of preparatory work carried out separately at their two institutions. But founding a collaboration does not mean building a detector. There was still the need to convince funding agencies, the American Congress, and a deeply skeptical scientific community. For years, funding requests ran into a wall. High-energy physicists, accustomed to particle accelerators, were skeptical. Traditional astronomers did not quite understand this instrument that resembled nothing they knew. Voices were raised saying the money would be better spent elsewhere. In 1986, the NSF funded a first feasibility study. The conclusions were encouraging, but insufficient. It was not until 1990 that the National Science Board approved construction. In 1991, Congress voted the first credits. In 1992, the Hanford and Livingston sites were chosen. In 1994, Barry Barish was appointed director and completely reorganized the project's management. The facilities were built between 1994 and 1998. The instruments were installed and commissioned between 1999 and 2002. The first scientific data run began in 2002. No one expected an immediate detection. It was known that the initial sensitivity was insufficient. But data were taken, the instrument was learned, noise sources were identified, and things improved continuously. Between 2002 and 2010, several observation campaigns succeeded one another. Silence. No signal. Nothing. In 2010, LIGO was shut down for a deep renovation, intended to multiply sensitivity by a factor of 10. This meant that the volume of universe being surveyed would be multiplied by 1,000. The effective range expanded from a sphere 100 million light-years in radius to a sphere 1 billion light-years in radius. Within this enlarged sphere, events capable of producing detectable signals suddenly became far more numerous. The upgrades were called Advanced LIGO. They took 5 years. The two instruments resumed observations at the beginning of 2015, and it was in September of that year that everything changed. Because throughout all those years, hundreds of researchers had dedicated their careers, sometimes their entire lives, to an instrument that had detected nothing. Engineers who had spent decades polishing mirrors, adjusting suspensions, hunting microscopic noise sources. Physicists who had begun their doctoral work believing detection would happen in their lifetimes, and who retired without ever hearing it. This collective obstinacy in the face of silence, this faith in something no one had ever seen, is one of the great stories of modern science. And what makes it even more beautiful is what happened on the morning of September 14th, 2015. Advanced LIGO had just resumed observations. The equipment was new, the detectors had been improved, but official scientific observations had not yet begun. The system was in a commissioning phase. On that Monday morning, at 4:50 in the morning local time in Livingston, Louisiana, the interferometer mirrors began to oscillate. The signal lasted only a fraction of a second. It rose in frequency, rose in amplitude, then disappeared. A few thousandths of a second later, precisely the time light takes to travel between the two sites, the mirrors at Hanford, Washington, oscillated in the same way. The computer analyzing the data in real time detected a coincidence between the two sites in less than 3 minutes. It sent an automatic alert to all members of the collaboration. It was Marco Drago, an Italian postdoctoral researcher at the Max Planck Institute for Gravitational Physics in Hanover, who received the alert first in Europe. The signal arrived at lunchtime across the Atlantic. He looked at the signal. He saw something that seemed too perfect, too good to be true. Within the LIGO collaboration, artificial signals are sometimes injected into the system to test researchers' ability to identify them. Only 4 people in the entire collaboration know when these injections are made, and Drago was not one of them. When researchers at the LAL in France returned from their lunch break and read the alert, their first instinct was the same. According to accounts from the CNRS, one of them said, "The signal looked too good to be true. It was so strong, it was visible to the naked eye." An hour after the alert, a second message arrived from Drago. This was not an artificial injection. The LIGO instruments were not yet equipped for such injections in advanced mode. Everything had worked correctly. What the detectors had recorded was a signal rising in frequency and amplitude over about 1/5 of a second, like the chirp of a bird climbing toward a high note. This chirp, the term astrophysicists use for it, is exactly the waveform that theorists had predicted for decades. 2 massive objects spiraling toward each other at ever-increasing speed before merging in a final instant. The shape of the signal allows the characteristics of the source to be recovered. 2 black holes, one weighing about 36 solar masses, the other about 29, located more than 1 billion light-years away. They merged into a black hole of 62 solar masses. 3 solar masses are missing from the balance sheet. Those 3 solar masses were converted into pure energy, carried away by gravitational waves in a fraction of a second. During that instant of merger, the radiated power exceeded 10 times the combined luminosity of all the stars in the entire observable universe. And all that reached the Earth, after more than 1 billion years of travel, was a shiver of space-time, tenuous enough to make LIGO's mirrors oscillate by an amount far smaller than the nucleus of a proton, but enough to be heard. The signal is named GW 15914, GW for gravitational wave, followed by the date of detection. The official announcement was made on February 11, 2016, after 5 months of exhaustive verification. The scientists wanted to be certain. They were. The probability that this signal was due to a random fluctuation of noise would be one in several hundreds of thousands of years of continuous observation. But now that we know this collision truly occurred, and that we captured its whisper, one question imposes itself. What exactly happened at the site of the merger? What unimaginable violence can convert the mass of 3 suns into a ripple of space-time in barely 1/5 of a second? And why, despite this colossal energy released, did the Earth feel nothing more? 3 solar masses converted into pure energy in a fraction of a second. That deserves a moment's pause, because the numbers alone say nothing. One must truly visualize what happened at that precise point in space, at that precise moment. Take a normal star, the Sun, for instance. It has been burning for 4.5 billion years. It will burn for another 5 billion years. And over its entire life, it radiates a colossal amount of energy in the form of light and heat, every second, without interruption. Now take the equivalent of 3 such suns, and ask yourself how long it takes the sun to radiate that amount of energy. The answer is about 75 billion years. That is 5 times the current age of the universe. And all of that, GW 15914, released not in 75 billion years, not in 1 billion years, not in 1 million years, but in 1/5 of a second. At the moment of merger, the power radiated in the form of gravitational waves was such that in just a few milliseconds, the 2 black holes radiated more energy than our sun will emit over its entire lifetime. But radiated as gravitational waves, not as light. That is why no one saw anything that night. What happens physically in that instant of merger? In the final moments before contact, the two black holes approach each other at a speed nearing half the speed of light. These are no longer objects moving through spacetime. They are objects that are themselves extreme distortions of spacetime, and when two such distortions collide, spacetime itself shatters. The collision resembles nothing one can see on Earth, or even in any other astrophysical event. There is no surface, no explosion in the conventional sense. The two event horizons merge. In an infinitely brief instant, the two singularities become one. The space-time around them reorganizes into a new geometry. And this violent reorganization sends a cry in all directions at the speed of light. A theoretical physicist proposed an analogy that helps convey the energy released. Imagine you are trying to bend a very rigid steel bar. You push, and the bar resists. Then suddenly, it yields. All the energy accumulated in that resistance is released in a fraction of a second, in the form of a wave propagating through the metal, a noise, a vibration. Space-time is like a cosmic steel bar, but of a rigidity that surpasses imagination. For millions of years, the two black holes curved and distorted space-time around them as they spiraled toward each other. The merger releases all that accumulated tension in one instant. The cry is called a gravitational wave. Why was the Earth not devastated? Because space-time is precisely too rigid. This rigidity is both what makes gravitational waves so hard to detect and what makes them so harmless. For a gravitational wave to deform your body in a perceptible way, the source would have to be incomparably closer and more powerful still. The Earth and everything on it were traversed by this wave, compressed and stretched slightly for a brief instant, and then everything returned to normal. Exactly as if you were standing in water, and a wave too small to knock you over passed under your feet. The event curved the space between LIGO's mirrors by a distance thousands of times smaller than an atomic nucleus. That is all that remains after more than 1 billion years of travel from a source whose power exceeds anything the universe has ever produced in light. And that is enough to tell a story. The physics of that instant of merger, once extracted from the signal, reveals extraordinary details. The respective masses of the two black holes, their spin rates, the distance separating them in their final moment, the mass and spin of the resulting black hole. All of this information is encoded in the few tenths of a second of the chirp signal, like the unique signature of a unique event. And reading that signature is not a footnote. It is the beginning of an entirely new way of reading the universe. A way that would find its most spectacular confirmation 2 years later, during an event that bore no resemblance to GW 150-914, and that would, for the first time, give gravitational waves a visible counterpart. August 17, 2017, is a Thursday. It is 12:41 in the afternoon, Coordinated Universal Time, when the 3 active gravitational wave detectors that day, the 2 LIGOs and Virgo, which had just joined the network, simultaneously detect a signal of remarkable duration, nearly 100 seconds. That is long. Black hole mergers last only a fraction of a second. 100 seconds indicates that the objects involved are far less massive, that they are spiraling far more slowly toward each other before the final merger. The analysis is immediate. The masses are on the order of 1 to 2 times that of the Sun. These are not black holes. These are neutron stars. A neutron star is the densest object in the universe after a black hole. It is the compressed core of a massive star that exploded as a supernova. The entire mass of a star, roughly 10 times heavier than the Sun, concentrated in a sphere about 12 kilometers across. The density is such that a teaspoon of neutron star material would weigh as much as all the mountains on Earth combined. These extraordinary objects contain matter in a state that no laboratory will ever be able to reproduce. And when 2 of them merge, something fundamentally different happens compared to 2 black holes. Neutron stars are not black. They have matter, and when they collide, that matter is ejected into the surrounding space in a visible explosion. 1 second and 74 hundredths after the gravitational wave signal, a gamma-ray burst was detected by the Fermi Space Telescope and by the Integral satellite, in the same direction of the sky. This delay of roughly 1 3/4 seconds corresponds to the time it takes light to escape the dense environment of the collision after the merger. In less than 2 seconds, two completely different types of signals, gravitational waves traveling through spacetime and gamma rays traveling through space, both from the same event, had been captured. The alert spread immediately through the worldwide astronomical community. What followed is one of the greatest coordinated observational hunts in the history of astronomy. Within hours, dozens of ground-based and space observatories pivoted toward the region of sky that the gravitational waves had localized, thanks to triangulation between the three detectors. This narrowed it to a region small enough to be scrutinized. 10 hours and 52 minutes after the gravitational detection, the SWOPE telescope at the Las Campanas Observatory in Chile spotted a new light source in the galaxy NGC 4993, about 130 million light-years away. It had not been there the night before, and it matched exactly what theorists had predicted as the result of a neutron-star merger, a kilonova. In total, 70 observatories on the ground and in space participated in this unprecedented follow-up. A kilonova is an explosion, 1,000 times more luminous than an ordinary nova, but far less luminous than a supernova. It occurs when the debris from the neutron-star collision is ejected into space at a speed approaching 1/5 of the speed of light, carrying with them material whose richness in free neutrons is unmatched in the universe. And it is there that something extraordinary is revealed about the very chemistry of our daily lives. In the days following the detection, spectroscopic observations of the kilonova revealed a characteristic signature. The light from the explosion changed color rapidly, shifting from deep blue to deep red over a few days, far faster than any other known stellar explosion. This spectacular evolution is the signature of heavy chemical elements, elements that can only be forged in an intense flux of free neutrons, a process nuclear physicists call the R process, for rapid. In this process, atomic nuclei capture neutrons so quickly that the laws of radioactivity do not even have time to correct their trajectory. The result is unstable nuclei that then slowly decay while releasing energy, and this radioactive decay is precisely what makes the kilonova glow red for days. Among the elements produced in this kilonova, gold and platinum and strontium, whose presence was confirmed with certainty in the spectrum of GW 170,817. For decades, astrophysicists knew that these elements cannot be manufactured in ordinary stars or in classical supernovae. The usual processes stop at iron. To go further in the periodic table, you need this neutron flux that only the collision of neutron stars can produce. And now, for the first time, we saw it with our own instruments. The ring you may be wearing on your finger right now, if it is made of gold, contains atoms that were forged in the collision of two neutron stars, somewhere in the universe, billions of years ago. Gold is not a terrestrial curiosity. It is a remnant of cosmic catastrophes. GW 170,817 founded a new branch of astronomy. It is called multi-messenger astronomy. The idea is simple. The universe sends us information in radically different forms. Light in all its variations, from gamma rays to radio waves, passing through visible light, infrared and X-rays. Neutrinos, those ghosts that pass through matter barely touching it. Cosmic rays, those particles of prodigious energy that travel millions of light years. And now, gravitational waves. For almost the entire history of astronomy, we used only one of these windows: electromagnetic light. It was like listening to an orchestra while only hearing the strings. Now, we hear everything, and the difference is staggering. Each messenger reveals something the others cannot show. The gravitational waves from GW 170,817 gave the masses of the two stars before the merger, their distance, the parameters of their orbit. The gamma-ray burst confirmed that some short gamma-ray bursts are indeed caused by neutron-star mergers, a question debated for decades. The kilonova proved that the R process takes place in these mergers. Radio waves detected weeks later allowed the geometry of the ejected matter jet to be reconstructed. Together, this information forms a picture that no single message alone could have painted. And since this founding event, the global astronomical community has reorganized its alert protocols to be able to reproduce this coordination for every new gravitational wave signal likely to have a luminous counterpart. But what GW 170,817 revealed goes even further. Thanks to it and to similar events, gravitational waves are telling us a story about black holes themselves that contradicts some of our most firmly established intuitions. Before September 14, 2015, stellar black holes, those born from the death of massive stars, had never been directly observed in the act of merging. There was indirect evidence for their existence: mass measurements from luminous binary systems, images of their effect on neighboring stars, but a lone, silent black hole, without matter to illuminate it, was invisible. The only way to see one was precisely when it was doing what a black hole does best: destroying and swallowing. And even then, what was observed was the light of infalling matter, not the black hole itself. With LIGO, for the first time, one observes the black hole itself directly, not through the light of what surrounds it, but through the ripples it creates in space-time by its mere presence and motion. And what these observations reveal is unsettling. When examining the first comprehensive catalog of detected events, covering the first years of LIGO and Virgo operations, several anomalies immediately stand out. First, the masses. The stellar evolution models we had built over decades predicted that stellar mass black holes should form primarily within a relatively narrow range of masses. Not too small, as neutron stars already occupy the lower end, and above all, not too large. Beyond a certain threshold, a particular instability in the cores of massive stars, called pair instability, should prevent black hole formation by completely destroying the star during the explosion. This forbidden zone extends roughly from 60 to 130 solar masses. And yet, GW 190,521, detected in May 2019, showed the merger of two black holes, one of which fell within this forbidden zone, and the result was a black hole of 142 solar masses, belonging to a so-called intermediate class that had been theorized but never directly observed. In November 2023, GW 231,123 broke all previous records, with two black holes whose individual masses each exceeded 100 solar masses, and which was spinning at a speed approaching the theoretical maximum limit. These objects should not exist, according to our standard models of stellar evolution. Their presence forces theorists to consider alternative scenarios. Perhaps these black holes are themselves the product of previous mergers in particularly dense environments, such as the cores of globular clusters or the accretion disks of supermassive black holes. Perhaps our understanding of the end of life of very massive stars is incomplete. In March 2026, the LIGO-Virgo-CAGRA collaboration published a new catalog listing 128 new events observed during just the first phase of the fourth observing run. More than 100 black hole mergers in less than a year. What was once a unique miracle has become routine. Mergers are being detected almost every week, and each new detection adds an entry to our atlas of black holes, revealing a diversity of masses, spins, and orientations that far exceeds what theorists had anticipated. We are not resolving mysteries. We are discovering new ones, at a pace no one had foreseen. There is also the mystery that persists regarding the very nature of the objects involved in certain mergers. Several events show objects whose masses fall in a murky zone between the heaviest neutron stars and the lightest black holes. Before LIGO, this zone appeared empty. Classical astronomical observations had found nothing there. Now, gravitational waves are revealing objects there whose nature is not known with certainty. Very light black holes? Extraordinarily heavy neutron stars? Something else? And to identify them, one needs not only to measure their mass, but to understand how fast gravitational waves themselves travel, because that speed carries fundamental information. GW 170,817 brought the answer to a question physicists had been asking for decades, with a precision no one had previously achieved. Do gravitational waves travel at exactly the same speed as light? In Einstein's general relativity, the answer is yes, by definition. But many alternative theories of gravity, proposed to explain certain unresolved cosmic phenomena, such as dark energy or the accelerating expansion of the universe, predict that these two speeds could differ slightly. Even a minuscule difference, accumulated over millions or billions of years of travel, would lead to a time offset between the gravitational waves and the gamma rays from the same event upon arrival. What was measured on August 17, 2017, settled this question in a striking way. The gravitational waves and the gamma rays arrived with an interval of 1 second and 74 hundredths, after traveling together this immense distance from the galaxy NGC 4993. This delay of roughly 1 3/4 seconds is perfectly compatible with the known physics of the source, the time it takes for gamma rays to escape the dense environment of the merger. If the two types of signal had traveled at slightly different speeds over such a long journey, the arrival offset would have been several days, or even months. They arrived less than 2 seconds apart. Gravitational waves travel at the speed of light. The precision of this measurement is without precedent in the entire history of physics. This confirmation has spectacular consequences. Dozens of alternative theories to general relativity that had been proposed to explain the acceleration of cosmic expansion were eliminated in a single measurement. If your theory predicts that gravitational waves travel at a speed different from that of light, even by the tiniest fraction, GW 170,817 invalidated it. It is a confirmation of Einstein that goes far beyond what any laboratory experiment can achieve. And at the same time, it raises new questions. If gravitational waves travel at exactly the same speed as light, this means the graviton, if this hypothetical particle exists, must have zero mass, just like the photon. Any theory attributing to it even an infinitesimal mass is eliminated. The universe is even more constrained than we thought. And yet, certain enigmas persist. Dark energy, dark matter, the Hubble tension. These mysteries call for new instruments, capable of hearing signals that LIGO cannot yet perceive. To understand why LIGO has limits, think about music. If you have a string instrument, it can only produce certain notes, determined by the length and tension of the strings. Ground-based detectors like LIGO are sensitive to a fairly high range of frequencies, between about 10 and a few hundred oscillations per second. This is perfect for mergers of stellar mass black holes and neutron stars, whose final seconds of spiraling generate precisely these frequencies. But there are other categories of gravitational waves, far lower in frequency, and therefore completely inaudible from the ground. These low frequencies correspond to events of even greater violence and even greater mass. The merger of supermassive black holes, those residing at the centers of galaxies, which can weigh millions or billions of times the mass of the Sun. When two galaxies merge, their supermassive black holes eventually approach each other and, finally, merge too. This event releases energy that dwarfs anything LIGO can detect, but at a frequency so low that a detector the size of a solar system would be needed to hear it. That is exactly what the LISA mission will be, an acronym for Laser Interferometer Space Antenna. LISA is a project of the European Space Agency in collaboration with NASA, with a planned launch in 2035. It consists of 3 satellites forming an equilateral triangle in orbit around the Sun, following the Earth in its annual journey, about 50 million kilometers behind our planet. The distance between each satellite will be 2.5 million kilometers, more than 6 times the distance between the Earth and the Moon. These 3 satellites will exchange laser beams between themselves, measuring the distance variations caused by the passage of gravitational waves at frequencies that ground-based instruments simply cannot perceive. What LISA will be able to hear will radically transform our understanding of the universe. First, the mergers of supermassive black holes. When 2 large galaxies collide, which happens regularly on cosmic scales, their central black holes eventually enter orbit around each other and slowly spiral toward final merger. This process can last millions of years, and throughout that time, it emits gravitational waves at frequencies LISA will be able to detect. LISA may see such mergers occurring billions of light years away, giving us access to a part of cosmic history that light cannot reach, because distant galaxies are opaque at certain light frequencies. Furthermore, LISA will hear pairs of white dwarfs within our own galaxy, millions of compact binaries emitting gravitational waves continuously at stable frequencies, creating a kind of gravitational background hum characteristic of the Milky Way. That hum itself is a source of information about the structure and history of our galaxy. But LISA's ultimate objective, the one that makes cosmologists dream, is to listen for primordial gravitational waves, those that may have been generated in the very first instance of the universe, during phase transitions in the ultra-hot matter of the newborn cosmos, or during even more exotic events linked to cosmic strings or other relics of high-energy physics. These waves would be the oldest witnesses in the history of the cosmos, emitted long before the first star ignited, before even atoms had formed. The oldest light we can see, the cosmic microwave background, shows us the universe as it was 380,000 years after the Big Bang. Primordial gravitational waves, if they exist and can be detected, would show us the universe in its first fractions of a second. But waiting for LISA does not mean we have no news at low frequencies. There already exists another type of gravitational detector, of a radically different design, that operates today and has already produced its first major discovery. This detector is not built in a laboratory. It extends across the entire galaxy, and it uses dying stars themselves as sensors. Pulsar timing arrays use millisecond pulsars, neutron stars spinning hundreds of times per second with extraordinary regularity, as a gallery of natural clocks scattered throughout the Milky Way. If very low-frequency gravitational waves cross the galaxy, they slightly modify the arrival time of signals from these pulsars. Slightly, but in a coherent, correlated way across all pulsars in the network, according to a specific pattern predicted by general relativity, called the Helling-Downs correlation. In June 2023, 4 international pulsar timing collaborations, Nanograv in North America, the EPTA in Europe, the PPTA in Australia, and the INPTA in India, simultaneously published their results. In a coordination reminiscent of the announcement of GW150-914 in 2016, they had all found the same thing, evidence of a common gravitational signal showing the characteristic signature of the Helling-Downs correlation. This was not a single violent event like the merger of 2 black holes. It was a background, an ambient murmur, omnipresent, continuous, coming from everywhere at once. A low-frequency hum running through the entire galaxy, always. And that hum, what is it made of? This is where the story becomes truly vertiginous. The hum that pulsars captured in 2023 is not the signal of a single event like the merger detected in 2015. It is something fundamentally different. It is the sum of everything. Imagine you are standing in a large city at night, far from any building, and you listen carefully. You do not hear one voice, one precise conversation, one particular engine. You hear the murmur of the entire city, an inextricable superposition of thousands of simultaneous sounds, adding up into a continuous, indistinct, omnidirectional background. That is exactly what the stochastic gravitational wave background is. It is the murmur of the entire universe. Every galaxy in the observable universe contains a supermassive black hole at its center. These monsters weigh between 1 million and several billion times the mass of the Sun. When 2 galaxies merge, which happens regularly on cosmic scales, their central black holes eventually find themselves in orbit around each other, slowly spiraling toward their final merger. This process can last tens of millions of years. During all that time, they emit gravitational waves, but at a frequency so low, so slow, that the waves themselves have wavelengths of several light-years. A single oscillation takes several years to complete. These waves are completely inaudible to LIGO, whose 4-kilometer arms cannot even begin to perceive them. But they slightly deform the space between the stars of our galaxy, imperceptibly altering the distances, and therefore the travel time, of radio signals from pulsars. What pulsar timing networks captured in 2023 is the superposition of all these sources. Thousands of pairs of supermassive black holes simultaneously merging in galaxies spread billions of light-years in every direction. An ambient gravitational background, a low-frequency hum that permanently traverses the entire Milky Way and, through it, all the matter of the visible universe. It is a discovery that, in itself, opens a window onto something inaccessible by any other means: the history of galaxy formation. The reason is as follows. The amplitude and characteristics of this background depend on the number of supermassive black hole mergers that have occurred in the universe, their distribution in mass, the frequency with which galaxies have merged over cosmic time. This background is therefore a kind of fossil imprint of the history of galactic structure assembly. By listening to it with sufficient precision, one can travel back in time and constrain models of galaxy formation. One can test theories about how supermassive black holes grew, about how the large-scale structures of the universe formed from the quantum fluctuations of the Big Bang. And perhaps, if this background has a component of primordial rather than astrophysical origin, it could carry information about the physics of the very first fractions of a second of the universe's existence, at energies no particle accelerator will ever reach. The most natural hypothesis is that this background comes from supermassive black hole mergers, but other sources are possible and are the subject of intensive analysis. Cosmic strings, theoretical filamentary structures formed during phase transitions in the early universe, phase bubbles formed during the first instance of the Big Bang, or even primordial black holes formed in the moments following the birth of the cosmos. Each of these sources would leave a slightly different imprint in the spectrum of the background, and the more data the pulsar networks accumulate, the more precisely that imprint takes shape. In this sense, the detection of the stochastic background in 2023 represents, for low-frequency gravitational physics, what GW 150-914 represented for high frequencies in 2015. It is a beginning. A new sense has just awakened. And to understand what all of this means for our vision of the universe as a whole, one must step back and look at what we have accomplished since that September night in 2015. For almost the entire history of astronomy, we have had only one sense for perceiving the cosmos: sight. And even that was very limited, because the human eye is sensitive to only a tiny fraction of the electromagnetic spectrum. By extending our vision to X-rays, radio waves, infrared, and gamma rays, we progressively enriched that picture. Each new spectral window revealed phenomena invisible in the others. Active black holes were invisible in optical light, but cried out in X-rays. Supernova remnants glowed in radio waves. Cold interstellar clouds lit up in infrared. But all of that was still light, always light, in one form or another. Gravitational waves are something radically different. Unlike light in all its forms, they do not carry photons. They do not propagate through space. They are a deformation of space itself, the structure in which light and matter exist. They carry information about regions of the universe that light cannot cross because matter is too dense or too opaque. They can tell us about events predating the birth of the first stars, predating even the formation of the first atoms, because at those epochs, the universe was opaque to all light, but transparent to gravitational waves. They give us access to the interior of the densest objects that exist, black holes and neutron stars, where no light can escape. That is why some scientists compare this revolution to the invention of an entirely new sense. Before 2015, all our astronomy was like watching an orchestra through a soundproof window. You could see the musicians moving, the bows striking the strings, the percussionists hitting the cymbals. You could deduce a great deal about what was happening, but you could not hear the music. Since 2015, the window has been broken. And in 2017, with GW 170,817, we learned to look and listen at the same time. The result has a richness that was not anticipated. The fully multi-messenger dimension of this new astronomy goes beyond the simple combination of gravitational waves with light. It also involves neutrinos, those phantom particles that pass through matter almost without interacting with it, emitted in colossal quantities during certain violent cosmic events, particularly core collapse supernovae. If ever a massive star explodes as a supernova in our galaxy, neutrinos will arrive on Earth several hours before the light from the explosion, because they escape from inside the collapsing star long before light can pierce the stellar envelope. Combining this neutrino signal, the gravitational waves from the collapse, and the light from the subsequent explosion, we will have a three-dimensional view of one of the most violent events in the local universe. The worldwide astronomical community is actively preparing for this opportunity. While waiting for that hypothetical galactic supernova, the practice of multi-messenger astronomy is developing rapidly. Automatic alert networks send real-time notifications worldwide whenever a gravitational wave is detected. Hundreds of telescopes, on the ground and in space, can pivot automatically toward the region of sky pinpointed by the detectors. International coordination protocols ensure that the broadest possible electromagnetic spectrum is scrutinized in the minutes and hours that follow. This planetary infrastructure, which did not exist before 2015, has become one of the most sophisticated scientific infrastructures ever built by humanity. And it is only beginning to reveal its potential. For at the heart of this multi-messenger revolution lies one of the most fundamental questions contemporary cosmology can pose. At what rate is the universe expanding, and why do different methods for measuring this rate disagree? Here is the problem. The universe has been expanding since the Big Bang. This expansion can be quantified by a number called the Hubble constant, named after the American astronomer Edwin Hubble, who first measured it in the last century. This number tells us how fast galaxies are receding from each other as a function of their distance. Measuring the Hubble constant allows us to reconstruct the history of expansion, understand the role played by dark matter and dark energy, and even predict the ultimate fate of the cosmos. The problem is that two major families of methods for measuring this constant give results that disagree, and the discrepancy is too large to be attributed to measurement errors. The first family starts from the cosmic microwave background, the oldest light in the universe, and traces the history of expansion from the very beginning. It gives one value of the Hubble constant. The second family directly measures the distances and velocities of nearby galaxies, using variable stars and supernovae as distance markers. It gives a significantly higher value, and neither the Hubble Space Telescope nor the James Webb Space Telescope, which confirmed its predecessor's measurements with even greater precision, has managed to close this gap. This gap, which cosmologists call the Hubble tension, is one of the greatest enigmas in modern physics. If it is real, and everything points to it being so, then either our standard model of cosmology is incomplete, or there is new physics we have not yet discovered. This is where gravitational waves enter in an entirely new way. From the very detection of GW 170,817, it was possible to extract the distance of the source directly from the gravitational waves, without using any astronomical distance standard. This capability rests on a remarkable property of the merger signal. The amplitude of gravitational waves decreases with distance in a predictable and calculable way from general relativity alone. By combining this gravitational distance with the optically measured recession velocity of the host galaxy, one obtains a measurement of the Hubble constant completely independent of the two conflicting families of methods. Gravitational waves are standard sirens, to use the technical term. They carry their own measuring ruler within themselves. The measurement from GW 170,817 was still burdened with too large an uncertainty to settle the matter, but as the number of detections grows, as each new kilonova or merger with a luminous counterpart adds a data point, the precision improves. And teams are even using the stochastic gravitational wave background, the superposition of all unresolved mergers, as an additional independent measurement through what is called the stochastic sirens method. Calculations indicate that in the years ahead, this method could achieve sufficient precision to finally resolve the Hubble tension. If the value obtained from gravitational waves aligns with one of the two families rather than the other, it will be an unambiguous verdict. If it falls between them or elsewhere, it will open the door to an even more profound revision of our cosmology. What all of this ultimately means is vertiginous to contemplate. Barely 10 years ago, we had never directly observed a gravitational wave. We had never heard the sound of a black hole merger. We had no way of seeing the universe other than in light. Today, we have a catalog of several hundred mergers. We have heard the background hum of all the supermassive black holes in the observable universe. We have watched gold being forged in the instant of a cosmic catastrophe. We have measured the speed of gravitational waves with a precision that has eliminated dozens of alternative theories to Einstein. We have discovered black holes that, according to our theories, should not exist. And we are beginning to use these waves to measure the rate of expansion of the universe in a way no one had ever been able to before. Science often has a habit of answering one question by raising 10 new ones. Gravitational astronomy is no exception to this rule. It has brought us answers we had been waiting for over a century, and it has opened abysses of questions whose existence we did not suspect. The black holes in the forbidden zone, the exact nature of the stochastic background, the mystery of the Hubble tension, the possibility of primordial waves from the Big Bang itself, all of this lies before us, not behind. The universe was not silent until 2015. It had always been speaking. It was our ears that were missing. We have just opened them. What we will hear in the decades to come could change our vision of reality as radically as Galileo changed the vision of the cosmos when he first pointed his telescope toward the sky. The difference is that this time, we are no longer simply looking, we are listening. If this exploration of one of the deepest scientific revolutions of our time has fascinated you, help us continue by hitting like and subscribing to the channel. Every subscription truly counts and allows the channel to produce new videos on the great mysteries of the cosmos. And if you would like to support the channel's development more directly, you will find a link in the description to make a donation. It is precious help that allows us to continue this work. Tell me in the comments, which city are you watching this from? And what time is it where you are right now?